I'm just going to be talking about indexing all the things, building your Elastic search engine in Python. So first, a little about me. I'm a senior backend engineer at Jopwell. For those of you that don't know Jopwell, Jopwell is a diversity hiring platform. So we're focused on helping underrepresented minorities, specifically Black, Latinos, and Native Americans find jobs. I've been a Python programmer since 2009. I've also done some PHP, unfortunately, but we won't talk about that. I've been building scalable search and backend systems for about 2 years now, and I'm the author of various open source Python projects. Great, so first I'm going to set up the database that we're looking at. It's very simple structure. It's literally just a profile that has a first and a last name, a location, and it's all connected through one junction table that has the profile ID and the location ID. Very simple database setup. So, we're trying to find Carmen Sandiego in SQL. Okay, great. So this is what everyone wants to start off doing it. Well, if we wanted to, we could start off by using some like with wildcards. This is going to take about 91 seconds for 1 million records. It's kind of fast, but the accuracy isn't very good. And so you end up with a SQL statement looking something to that. You've probably done something like that before. So first name like Carmen and last name like San Diego. So again, it's okay, but it's not very accurate at all. Oh, but wait. We could also try using full text search. Oh, so it would look something like this. And this is for Postgres. There are some options to do it in MySQL as well. But not to start a flame war with MySQL people, but the tech support, the full text search in MySQL is quite lacking these days. And so that'll take you, 8 minutes on 1 million records to run that. And a little higher accuracy, still not that great. And then beyond that, there are some inverted index search utilities that are available through Postgres. One of the big problems with them is that, you get really large SQL statements. And that's not good at all because you have to maintain those. So it's definitely not scalable at all. Also, if you want to do any kind of distributed work with this, as you know, those of you that have worked with databases, you have to do all that sharding yourself. So let's just forget about doing that. Again, MySQL has very limited support for full text search. Also, another thing I want to mention is that some of the features that you want to do aren't always going to be supported on Postgres RDS. For example, if you want to do stuff like spelling correction, some fuzzy search, that's not going to be really supported if you're running all of your infrastructure on AWS, specifically using the Postgres RDS. And like I said, we're going to get a lot of long custom SQL queries. And we'll have to manage our own database sharding. So probably not a good solution. So enter Elasticsearch. It's built directly on top of the Lucene search library. It's already designed to be distributed from the ground up. They've already taken the time to do all that sharding and understanding like how your data is distributed, so you don't need to really worry about that. Also, it has full text searching, indexing, and it's a search engine as well. So they took one problem and decided to solve that, just search. It's great. And this is really nice. It has features a common interface. In our case, it's JSON over HTTP. That's something we're not going to get with multiple databases. Okay, so our challenge is to get the data from our database, traditional database, into a flat structure that's JSON that looks something similar to this. So we're taking the name, first name, last name, the locations that Carmen Sandiego has been, and we also want to have the ID so that when we take the data back out, we can use those IDs to look up the actual locations in our database. So given this structure right there, that's what we need it to look like. So we'll start off by flattening a database object. I have full code examples for all this, and I'll share that with you guys after the talk. But keep in mind, these are very brief ones just to illustrate exactly what's going on here. So we're basically just taking a profile and iterate over every single one of the field names inside of that profile and grab the value and grab the name of the field and then just add it to our very simple dictionary. And then at the end, we're going to end up with a nice dictionary that will eventually get converted into a JSON blob. We'll send that to Elasticsearch. But you ask, what about data in related tables? Well, pretty simple actually. So we had Carmen Sandiego. She has a bunch of locations that she's traveled to. Very easy. We can just take our profile object and all the locations she's been to, iterate through those, add them to arrays, and then we'll just add that to our full dictionary at the end. It's very straightforward index. So all these examples are using Elastic Pi. It's a very nice wrapper that Elasticsearch has built around Elasticsearch, because you could do these calls to Elasticsearch in JSON using request library, but they've taken the time to make a really nice wrapper around it. So we're going to go ahead and use that. So that's literally all you have to do. You take the data that we saw at the beginning, so that JSON blob, send it in there, and then also we're going to submit a doc ID. That's actually very important. So we want to, so when we're taking our data out of our database, we want to use we want to have some way to be able to look up that data when we pull it out of Elasticsearch. So a very easy way to do that is to just set the ID from your database to be the exact same ID in Elasticsearch. Okay, so we've indexed our entire document, and now it's all in Elasticsearch. Great, we're going to perform our search now. So these are the steps we're going to go through. First, we need to perform our query to Elasticsearch. So say we're looking for Carmen Sandiego, that's our search query. Then we get our data back, and we found all the locations that Carmen Sandiego has been. We're going to grab the doc IDs from the search results. So in the results, you'll have all the locations that Carmen Sandiego has been, and those will each have doc IDs associated with them. And then we'll use those doc IDs to load the profiles from our database for our final results. And then return that to the end user. So again, we're going to be using Elasticsearch wrapper. It's very simple. And you basically, the same way that you're uploading documents, it's also going to be a JSON blob that you're going to send up to Elasticsearch for performing the query. So there's a lot of different queries you can do with Elasticsearch. We're going to go ahead and use the very simple query string, and we'll just be looking for Carmen Sandiego, and we're looking for specifically Carmen Sandiego within the fields of the first name and last name. So you can tell it, okay, I have a document that I've indexed into Elasticsearch. Maybe I only want to search over the first names and the last names. I don't really care about searching over the locations. So we can tell it specifically which fields we want to search over. We just make a very simple search. We tell it the name of our index. We have built up this JSON blob. And then similar to, for me, those of you that deal with traditional REST, you have limit and offset. And we can also say, send that in as well, because, oh great, we want the search results, but we don't want all of the search results at one time. So we want to paginate through that. And so we'll just put in like how many results we want at a time, and then which page of those results we want. So it comes back looking something like this. So we searched for Carmen Sandiego, and we came back with the document Carmen Sandiego, all the locations she's been, and New York, London, and Tangier, and the IDs for those. Okay, great. So we got the search results back in this JSON blob. We need to prepare it so that we can actually return that to the user. So this is the other part that I was speaking about, is that we need to take those IDs from the document and pull back the actual profiles that we have saved in our database. So we can just do a simple query, a get query based on the ID that we sent in, and that's the ID from the document, and now we can pull back that data from our database. Pretty straightforward. Okay, great. So now we know how to index all the documents. We know how to pull all the results back, bring our database object back. This is all great. Now we're going to try to do this in actual production. So these are more some like tips and tricks that I've learned for doing search in actually a production environment. First of all, many of you are familiar with Celery, if you've done some kind of distributed computing. But it's very simple. It's just a very simple distributed task queuing system. We want to use Elasticsearch, or excuse me, Celery for this because many of these indexing tasks are very memory bound. And if someone's accessing our website, we don't want the server to be tied up with, performing the search queries or doing the indexing. We want to be able to push that to this distributed task queue so that the main site can still receive traffic. And we'll break up the task of indexing every one of our new documents initially into Elasticsearch. So when we're indexing all the documents for our very first initial indexing, and then as we get more documents that are added, we can just add each of those in as a separate task. So this is a very simple code example, but we could have one master task, index all the docs, and each one of these instances would be processing a single doc, so indexing that single doc, and then we can go ahead and use group. So this is similar to some of you guys that have heard about an async IO. You can have a function that will allow you to not proceed to the next section of code until all of it's been finished. So you're waiting for that event to finish. So we can just use a group in Celery to do that. And then so as individual documents get added later, we would just call process docs and pass in the profile ID. And then for that master task, we would just call index all the docs. Awesome. So now some of the other challenges that you arise with, and kind of the meat and potatoes of this talk is, great, we have the data stored in two different locations. One of the biggest challenges is keeping these two data stores in sync. Because when people do a search result, they're going to want that data that comes back, they're going to expect that to maintain data integrity. And so we need to keep both of those data stores in sync. So really easy way to do it, if you're using the Jango, you can just override the save function. So you override the save function for your model, and you say, okay, go ahead and save the profile, take that ID, and start a task we call add doc, and we're going to add that to our search index. One other piece of information that I'm mentioning now is that say you have two of these indexers working on separate machines, and both of them gets the document at the same time. Now you have a race condition. So that's, we also need to think about that as well. It's not in this example, but if we did have many indexers running on different machines, we might run into a race condition like that, and so we might need to add some kind of locking structure to this. You can roll your own lock. For what we do at Jopwell, we store the locks in Redis, so we just do a simple write of the lock to Redis when we start the task, and then once the indexing is finished, we release the lock. That way, if you have multiple indexers running, you're not going to ever run into any of these issues. Okay, great. But what about partial updates? So we have this massive search document now, and it's okay when we have like a really small search document, but now we have these really large search documents. So now the idea of doing partial updates is actually really, really critical. It's supported. So it's very simple. You just call an update function, and you just pass in the data that's changing. One other thing to mention is this refresh equals true. So if you set refresh equals true, it's going to force Elasticsearch to refresh its index after you've made this update to it. You could also set that to false if you want it to update at a later time, for example. One thing I will mention about this update doc, we don't use this in our code base because any of you that have done work with the Jango, you know it's pretty tricky. Okay, great. What fields have changed on my database? So there's not any custom functionality. There are a couple of libraries to be able to find out specifically when I do that save, which fields have changed. So which fields are dirty, which ones are clean, and only basically update the dirty fields. There's not really functionality for that. There is some form of it through third-party libraries. But the problem with that starts to become, and you could use a lock to solve this, but like, okay, I found something dirty over here and something dirty over here, and I want to make both of those updates together. Which one overrides the other one? So you run into those same type of problems. You could use a lock to solve that, potentially, but in our experience, we found it easier to just go ahead and re-index the entire document. But if you start getting larger documents, you might have to think about strategies like that to allow you to do partial updates. Yeah, and so I have a link to the resources for this, a link to Elastic Pi, and the official docs for Elasticsearch and for Celery. Yeah. Any questions?
You can back to the last one.
Yeah. Okay. Any questions? Okay. Thank you.